Good morning, sir.
Good morning. Sometimes I'm discussing the same thing again and again, but because I think it is very critical for you to understand. Still, I may have to repeat a number of times with all these critical matters. Now, let us go through another new problem. What is the given in the problem is, with reference to the frame of the reference OXYZ, the following state of stress exists. Determine the principal stress and the associated vectors. Uh, Determine the principal stresses and their associated reactions. Also check the invariance of L1, L2, L3. Now, I'm just repeating very quickly. Here, we are always imagining the stress situation of a point in space along in relation to a rectangular axis in three dimension, OX, Y, and OZ, where O is the origin. And, and if we imagine a rectangular pyramid with origin O is one of its apex, and three out of four planes which we are supposed to have a rectangular pyramid, three is along this three coordinate axis. Then what happens? Uh, we'll have, as per Cauchy's theorem, the stresses in three direction, stresses given in three particular direction itself. Now, the main question is, that is the question of the theory of invariance. Invariance means if we change the original rectangular axis, what will happen to the coefficients of the equation of coming out from the Cauchy's theorems itself. And we have shown that if the axis changes, but invariance doesn't change, which axis changes, but the value of the original stresses, sigma x, sigma y, sigma charge remains unchanged, then the value of the invariance doesn't change. We have proved that in earlier verses. So here, what we have to do first, we have to find out the value of the invariance, that is 1, L1, L2, and L3. Next, we have to discuss the principal stresses and their directions, etc. Now, as per Cauchy's theorem, we put the values of invariance here, values of the coefficient here, like in a matrix, sigma x, tau xy, tau zx, tau xy, tau zx, sigma y, sigma z, sigma y, sigma z, etc. Now, as this matrix is given to us, so you can put this matrix side by side, and with the idea that sigma is equal to 1 and tau x is equal to 2, sigma is the 1 and 1, and so and so. So we know we have already reduced the equation for the invariance L1, which is going on equal to sigma 1, sigma x plus sigma y plus sigma z, which is equal to, put the value of sigma x, y, and z here, here, and here, which is equal to 1, 1, and 1. So 1 plus 1 plus 1 is equal to 3. And next L2, it is given by this matrix sigma x, tau xy, tau xy, sigma y. What is seen, which means it is a very clear understanding is that along one diagonal this sigma x and sigma y, and another diagonal tau xy with suffix x, it comes here, and suffix y also comes here. Similarly, you can remember the other two, sigma y, sigma z, suffix y, suffix z for tau. Now put all the respective values of sigma x, tau xy set it is here from this equation. The equation will take this particular from 1, 2, 2, 1, 1, 1, 1, 1, etc. And if we again simplify it, it will become L2 is become minus 2. Next. I don't know why we are reading the QR code. It is given clearly. Just 1 second. Just follow the QR code. I don't think there is any other problem here. Okay. Now, now from the equation, now invariance L3 will be given by this equation, which we have already proved, and put the value of 1, 2, 1, 2, 1, etc. And as a result, and we'll get the value of L3 is equal to -1 itself. So this equation become sigma 1, sigma 3 minus L1, L2 square, N1 as L1 minus sigma square plus L2 sigma minus L3 is equal to 0 itself. Or if we have further simplification here, we put sigma 3 plus 1 here, and between these two, sigma 3 sigma square minus 3 sigma, we put together as 3 sigma sigma plus 1. Thus, sigma 1 plus 1 become sigma plus 1, sigma minus 1 plus 1, etc. Thus, we get sigma plus 1 sigma square minus 4 sigma is minus 1 equal to 0. So, one solution is for sigma is -1, and other two solutions can be obtained by solving the quadratic equation here, that is sigma square minus 4 sigma plus 1, where a is equal to 1, b is equal to -4, and c is equal to 1. So we can simply put this value in sigma is equal to minus b plus minus square root of b square minus 4c divided by 2a, and get the value of sigma, another 2 sigma, sigma 2 sigma 3 as 2 plus square root of 3 and 2 minus square root of 3. So here, by solving this equation of through the A matrix, which is through the Cauchy's equations, we get three mutually perpendicular values of three values of sigma, sigma 1, sigma 2, and c or 3. Now we have to prove that whether these values are along the whether these are all principal stresses or not. Now, how will you do? Now we have to check the invariance. We thought that if it is, if we plot, if we just told you that if the initial stresses are known to us of three mutually perpendicular axes, or we can know the resultant stress and its component can resultant stress and its orientation and its cosine, that reaction cosines are known, then sigma x, sigma y, and sigma z can be calculated really. And we have to find the if the coordinate axis change, but the initial sigma x, sigma y, sigma z doesn't change, then the value, the effect of change in coordinate axis will not change the value of L1, L2, and L3, and they remain same. Thus, you see, we plot three values of sigma, sigma 1, 2, and 3. Now we put the quadratic equation here like this: sigma x minus sigma y, because we know uh, our principal axes are coinciding with our ox, y, and oz. Then what will happen? This sigma, and we know, as we are talking with the principal stress and strain, principal stress, and there is no shear stress acting over any of the ox, y, and oz plane. So all these shear stress here are becoming zero. Only the principal tensile stresses are available here. So the Cauchy's equation will be modified as sigma x minus sigma y, and tau x tau z even same as if in our original form there was as our original causes from the tau x, tau xy, tau zx, and tau yz are all available because they are not principal axis itself. So if we put this value here, value of sigma x here, which is only changing, then tau x and tau ny and reaction vectors are not changing at all. So this equation of Cauchy's theorem will take this particular form. And as we know, the value of sigma will be negative because it is opposite to the uh, positive direction of x-axis itself. And we have another equation for the cosine vectors, nx square plus ny square plus nj square is equal to 0, because the cosines of any angle subtended by the resultant stress from x and y and z, if we make a square and add together, that will become equal to 0 itself. Now, actually, this will be okay, n plus 1. Now, we put the value of sigma x, which is already given at the beginning of the problem, and put the value of sigma here as sigma minus 1. So the equation will become, take this form like this. Then this equation will take this form, 1 takes 1 plus 1, 2, 1, all these problems, sigma x and sigma you have put, but we don't know the value of, sigma and reaction cosines here. And we know that reaction cosines are equal to 1, not 0. It was wrongly written in the earlier page. So we have 4 equations, 3 reaction cosines here. And if we, so on the second and third equation, if we solve the idea that z is equal to 0, because third principal stress, principal stress is only along x and y axis, and z is there is no value in the z axis, then third and fourth equation we will have, this becomes nx and ny, equation of nx and ny. And if we solve, nx will be plus minus 1 by square root of 2, ny plus minus 1 by square root of 2 itself. They are more or less same. Hence, for sigma in the direction, sigma 1 is in the direction plus square root by 2 minus 1 by square root by 2 and 0. It should be noted that the plus and minus is associated with nx, ny, and nz, representing the same line itself. Next, if we go to sigma 2, which value is again 2 plus square root of 3, and follows the same procedure here, the coefficient will be 1 because we are subtracting 1 from 2. Then minus 1 minus 3, because from 1 we are subtracting this 2 minus square root of 3, then it becomes minus 1 minus 3, 2 nx ny and then z, and 2 nx ny and z. Same way we are putting the nz coefficient nx, ny and nz together. Now again we have the sigma to z, and z is, we see the third equation equal to 0 itself. Those nx and ny, second equation it will be equal to 0. Then nx and ny is equal to nx and nz will take this particular form of simplification. Now, for sigma 3, we'll have the same value for nx and y and z, I mean same process, and in a manner similar to our here, sigma z and sigma y is equal to 1 and 1 by square root by 3, half 1 minus square root of 3 to the power half itself. So this is the way we are getting the reaction cosines of the direction of the normal forces acting along the x, and which is normal to the principal axis itself. Here, for the principal axis, as if it is either maximum or minimum, and that exists, there is no stress. So plane normal to the axis is the carrying the normal plane, normal stress of the normal plane acting over it. Next, another problem. For the set given stress, determine principal stress and their direction itself, which is given as tau ij 0, 1, 1, 0, 1, 0. There is all stress, normal stress is sigma is 0 here, and only the tau r is there when shear stress exists, and they are also of same value in all directions. Let us see how does it works. Hmm. Now, if we solve in the same way, because sigma x plus sigma y is plus sigma z is equal to 0, all x, sigma y, sigma 2 is equal to 0, and for the matrix with sigma x, all L3 is equal to minus 3 and L2 is equal to minus 3 and L3 is equal to 2 itself. So here sigma, the function of sigma is equal to minus sigma 3 plus 3 sigma plus 2, or if we solve again by this equation, we'll have sigma plus 1 sigma multiplied by sigma minus 2 plus minus sigma plus 1 equal to 0 itself, and sigma 1 is equal to sigma 2 is equal to minus 1, and sigma 3 is equal to 0, 2. Since two of the three principal stresses are equal, and sigma 3 is different, then the axis of sigma 3 is unique, and every direction perpendicular to sigma 3 is a principal direction associated with sigma 1 is equal to sigma 2 for sigma 3 is equal to 2. So what is this here? Both sigma 1 and sigma 2 are equal, but sigma 3 has different value. So up to two central stresses are equal, then sigma 3 is different. The axis of sigma 3 is exactly unique, and every direction perpendicular to sigma 3 is a principal direction associated with sigma 1 and 2 and so. Thus, solving the earlier equation of sigma x, which is given as, so it will be minus 1, minus 2, and minus 2 everywhere, because they have the same thing, sigma x minus 6 minus sigma, where sigma is equal to 0, minus 1 equal to 0, and ny plus nz is equal to, this is all tau is, there is no value, ny nz becomes 0, this is becomes the 1 itself. Tau x1, tau xy is given in the matrix here, and 1 is also equal to 0 itself. Now, here it is minus 2, there is minus 2, both with a 0 associated value. And nx plus ny square plus nz square is equal to 0. This gives sigma y. Among this, solving this equation, we'll get sigma x plus sigma y plus sigma x is equal to sigma y is equal to sigma z, 1 by square root of 3. Problem number 3 is here. The state of stress at a point is such that sigma x, sigma y, all our stresses are equal to rho itself. Determine the principal stress and the direction. So here, from the given equation, if all the stress values are same, so L1 is equal to 3 rho, and L2 and L3 are all equal to 0. So this equation, so cubic equation, will take this particular form, sigma cube minus 3 rho sigma square to 0. And from the solution, we'll have 1 sigma 1 is equal to 3 rho, and other sigma 2 and 3 are equal to 0 itself. Now, if we put the value of sigma 1 by 1, sigma 1 is equal to 3 rho, then rho minus, this equation will be rho minus 3 rho minus 0. Here it is all rho, because we know this is given like this, and 3 rho means that equation will take this particular form. equation will take Cauchy's Cauchy's theorem will take this form -2 everywhere, and here at the end, everywhere rho is associated and right hand side is equal to 0, rho will be cancelled. So -2 plus ny plus nz, nx minus 2ny plus nz, nx plus ny minus 3nz is equal to 0. The above three equation gives us nx is equal to ny is equal to nz, with nx square plus ny square plus nz square is equal to 1, and one gets nx is equal to ny is equal to nz is equal to square root of 3. The above this equation, and along this equation, here we see nx and ny are all 0 or equal, and all are equal to 1 by square root of 3, 3 itself. Thus, on a plane that is equally inclined to x z axis, there is a tensile stress of magnitude 3 rho, which is the case of uniaxial tension. The axis of loading becomes making an equal angle with the same x, y, and z axis, because all these direction cosines are same. So if one denotes that loading axis is by z dash, is loading axis, then other two axes, x dash and y dash, can be chosen arbitrarily. The plane normal to this x, y, and y z plane are also stress-free itself. Now, there is another type. The state of stress referred to the principal stress itself. Now, what we are doing is expressing the stress of state at a point by 6 rectangular stress components. We may choose that the principal axis as the cosine axis and refer to the rectangular stress accordingly. Then we have the following matrix. So what we have, state of stress, 6 rectangular coordinate axes, 3 are tensile and other 3 are tau, and xy, tau xy is equal to tau xy is equal to tau yx, like this. So we have total 6 rectangular axes, and principal axis as the cosine axis and refer to the rectangular axis accordingly. And if principal axis is cosine axis, then all taus, all taus are means which are along this original rectangular axis, all the tau are 0, because on the principal axis all shear stresses are supposed to be equal to 0. In any one plane with normal n, the components of the stress vector are available from Cauchy's equation, and Tx to the power n here is sigma x nx, Ty to the power n is sigma 2 ny, and Tz is sigma 3 nz. Because there is no shear, so Tx is exactly the reaction cosine of the and Tx will be equal to the principal stress multiplied by the reaction cosine of the of this normal axis, Ty and Tz are same accordingly. The resultant stress has this following magnitude: T to the power n squared sigma square n square sigma 2 square ny square sigma 3 square nz square. If sigma is the normal and tau is the shearing stress on the plane itself, then what happens? The sigma is the normal and tau is the shearing stress on this plane. Then what happens? This sigma, the tau x1, tau t is equal to uh, tau minus tau square plus sigma square, where sigma is equal to sigma 1 nx square, sigma 2 n square, sigma 3 nz square itself. Now what happens? If we know that tau square is equal to Tn square, with this minus this sigma, this equation will take this particular form. So as tau square will be put sigma x here, then nx ny whole square tau sigma minus sigma y, and so we are just squaring this. This is putting this value, and sigma putting this value is also squaring it, and then put everything here, and this will take this particular form here. So sigma this one, sigma t to the power n, t square is equal to this equation, and sigma is equal to this equation. And if we square it and subtract from t, which is like this, then nx square ny square sigma minus sigma 2 sigma 1 minus sigma 2 here, and sigma 2 minus sigma 3 and sigma 3 minus sigma 4. This is the equation on sun, that is the equation for tau square. Thus these three invariants will assume the form thus the three invariants. The three invariants will assume the form sigma 1 plus sigma 2 plus sigma 3, sigma 2, L2 is equal to sigma 1 plus sigma 2 plus sigma 3, and L1 sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1, and L3 sigma 1 sigma 2 sigma 3 itself. Now invariance. Now let us discuss briefly the invariance which we are using here time and again. Consider the two rectangular coordinate system or frame of reference. Both you can say rectangular coordinate system and you can say frame of reference here. So that is one OX, y, Z, OX, OZ, OY, and OX, and another is O X dash, O Y dash, and O Z dash. So one reference is O X Y Z and one reference is O X dash Y dash Z dash, and having the origin O, but with axis rotated with respect to each other. But with the axis rotated to each other, just they have the same origin, but they just inclined one with the other itself, or rotated one with the other same. Now a point P here, somewhere in the space, the coordinates will be x, y, z, no problem, and for the next axis it will be x dash, y dash, z dash. So related to each coordinate system itself, this value or these coordinates of P will change accordingly. The equation for transformation between the coordinates of both the systems will be like this: x dash, say L11 x, L2, L3y, and L3z itself. The equation for transformation between the coordinates of the system are given like this. Here, x dash, relation between x dash and x, y, and z are given by this relation itself. Y dash, x, y, z like this, and with this L21, L22, L23, and y dash is given by x, y, z, and with this coefficient of x, coefficient of them, etc. Well, Lij is equal to j, where jk is 1, 2, 3 are the direction cosines of the x, y, z axis with respect to y, x, y, x. So what we are saying that again, what we are saying initially, the value of x, okay, if multiplied with the direction cosine of these coordinates with x dash, coordinates of x running coordinates of x dash, y dash, z dash, then you can multiply individually by a constant direction cosine, and we will get particular equation like this. In case the origin of the two coordinates are not coincidence, the equation of this transformer will become x dash is full equation plus a1 dash, full equation plus a1 dash, a2 y2 plus a2 dash z2 with this full equation plus a3, means a3 as these are the, where the origin of xyz is located at a1 dash, a2 dash, a3 relative to xyz. So the origin of x dash, y dash, z dash is given as a1 dash, a2 dash, and a3 dash. So we have to add with this equation to get the value of x and y, z, or the value of the coordinates x, y, z itself. So this equation is more or less proved here. Let us go to the next vector, next portion of our solution, that is mode circle. From the knowledge of our previous center of materials, we understood that other than the analytical method of calculating the principal stresses, we can have the geometrical construction or geometrical solution that brings out same important results. Say at a given point P here, this is given here, point P. Let the frame of reference is O, OXYZ as PXYZ is chosen along the principal stress itself. Let the frame of reference PXYZ is chosen along the principal axis. And now consider a plane. Consider a plane with normal n at point P. Then sigma will be the normal stress and tau is the shear stress. As per our earlier decision, for any point, the for the rectangular axis, a resultant will take place. Any resultant force takes place. It will it will be normal to certain plane, and the resultant stage also have some plane while over which is normal. If we say that plane is normal plane is equal to n. Let sigma be the normal stress and tau is the shear stress on this point. Let's take another axis for sigma and tau. In this place, we can make another axis for tau, sigma and tau. In this case, we can make the point Q, say here. We take another point Q with coordinates sigma and tau, representing the volume of the normal and shear stress on the plane N. For different planes passing through the point P, we get different values of sigma and tau. It is very clear. If axis changes, sigma and tau may change itself. We can take another point with coordinates sigma with coordinates tau x and y, represent the value of the normal and shear stress in the plane N. For different planes passing through the same point, we can get different value of sigma and tau. Corresponding to each plane, a point Q can be located with coordinates sigma and tau itself. The plane with the x-axis and the tau and tau axis is called shear plane. X-axis and tau axis is called shear plane because no numerical value is associated with the symbol itself. Pi is not 3.14; it's just a symbol. We are using it just a symbol itself. Problem now is to determine the bounds for sigma t, bound for sigma tau and c are all possible direction of any cell. Arrange the principal stress now. That algebraically sigma 1, 2 and 3 itself. Mark off sigma 1, sigma 2, sigma 3 along the sigma axis and construct the three-cycle with diameter sigma 1 minus sigma 2, sigma 2 minus sigma 3, and sigma 2 minus sigma 3. So what we have this axis at z, axis of sigma along the x-axis or along the horizontal, and tau along the vertical itself. Then we've got 3 points here. Three principal stresses points A, B, C. So this is the Y. A, this is the origin O, A, that is one is B, and that one is C. A is positive, B is also positive, but C is also negative. C is negative value. So what happens? Let the points A, B, C represent three principal stresses by three principal stresses, and the associated shear stress and are equal to 0 itself. Associated shear stresses are all equal to 0 as per our definition of principal stress itself. The maximum shear stress is equal to half sigma 1 by sigma 3. What is that? Difference between sigma 1 and sigma 2 divided by 2 itself. shear stress will plot it here, and sigma 1 is from 0 to A, sigma 2 is from 0 to A, so 0 to B itself. So if we plot this value, we'll get this triangle here where the maximum equation, maximum value of tau which is possible is equal to half sigma 2 minus sigma 3 equal to 1. Sigma 1 minus sigma 3 is equal to 1 itself, means from here to here, here to here. If this length varies, it will give you the value of normal stress itself. And associated normal stress is supposed to be plus sigma 1 and 3 from here, and this length plus this length divided by 2 will be comes from here itself. Now, as there are three maximum values of sigma 1, 2, and 3, as there are two maximum ABC represent the three principal stresses along three principal planes. Associated shear stresses are 0. What we are having, the normal shear stress is equal to half sigma 1 minus sigma 3, and the associated normal stress, maximum shear stress is half sigma 1 minus sigma 3, and associated normal stress half sigma 1 minus sigma 3, indicated by the point D on the top of the outer circle. As there are three maximum values sigma 2 and 3 and C, normal stress, there are three maximum values, 1 minus sigma 3 by 2, 2 minus sigma 3 by 2, and 1 minus sigma 2 minus 2. The plane on which these three shear axes acts is called principal shear planes, while the planes on which the principal normal stress acts are free of shear stresses. The principal shear planes are not free from principal normal stresses. The normal of stresses associated with the principal stresses are respectively sigma 1 plus sigma 2 by 2, sigma 2 plus sigma 3 by 2, and sigma 1 minus sigma 2 by 2. This is associated by DEF. Well, our time is more or less up. I can't go in more details. Yeah, there is.
हेलो सर.
So,
हेलो सर.
हाँ बोलो.
सर बोल रहे हैं सर, हम इनरोल नहीं है सर एलएमएस पोर्टल में.
কারোই হচ্ছে না.
हाँ सर.
किसी का होना नहीं. None of you are getting
सर
enrolled.
सर एलएमएस पोर्टल में इनरोल नहीं है सर, तो फिर अटेंडेंस कैसे बनाएंगे?
First time I am giving you the access of the portal.
QR code.
But you could not give the attendance. ठीक है?
Yes sir.
Let me see why it's so happening.
लैब का क्लास का दोनों का अटेंडेंस सेम है ना सर?
I have given the portal. Let us see that. Otherwise, I will give you the attendance from my sheet. Possibly you have this is just started. Your some more adjustment is required for LMS portal. ठीक है? Let me see. Okay. Goodbye.
Okay sir.
I have given all the attendance so far from my value itself.